Okay, we're back, and in this case we're looking at rotational motion, and something that we've done quite a bit of in just normal linear mechanics, which is equilibrium. In the past, when objects are free to move linearly, up, down, side to side, or at some angle, whether it's two-dimensional, three dimensions, we can do that pretty easily by balancing forces. We can break things up into components. We can look at x components and y components, and even z components in three dimensions, and just balance those. Typically we've used up equals down, right equals left. However, nowadays, when we get into rotations, you could have something like this picture, where you have this bar being held up by a string, and one end is fixed. Over on the left-hand side, there's like a hinge or something. There's an actual axis of rotation over here. And if you were to cut that string, not only would it fall, but it's going to rotate down. Now, if it's not rotating, that means that we have a condition where the torques are being balanced in addition to the forces being balanced. So I want to go through this example just kind of briefly and just kind of outline what this looks like when we have to include torques in the mix. It's kind of a new third condition for equilibrium. The notation I'm using up here is any kind of torque that's trying to make it spin clockwise is being balanced by other torques that are trying to make it spin counterclockwise relative to the axis of rotation. So we have to do that as well as the usual balancing the forces up and down and balancing the forces right and left. So here goes. Let's take a look at and see what this looks like. As always, the first thing you want to do is to make a force diagram. In this case, if the bar has some weight, in this case it weighs 4 newtons. On a force diagram, we label that at the center of mass of the bar. Okay, 4 newtons going down. And in this case, there's also an additional weight hanging off the end, another 5 newtons trying to pull it straight down. The string, of course, is pulling up on it, and so we have a tension force that we don't know. That's really the main thing that we're after, is to try to find that tension. And that's supporting it in the upwards direction. Okay, does that look complete? Well, I would say there's something going on at the wall as well. For example, part of the tension is trying to push this bar to the left into the wall. It's not moving that way, so there's probably some kind of like a normal force, I'll just call it Fx, pushing back on it. And because that edge is not falling or slipping down the wall, that hinge is probably producing some kind of upward force. I'll call it Fy, pointing upwards. Okay, so we have to assume there's something going on over at the wall as well because of the hinge. That's the complete force diagram. So let's set up what we're used to doing. Let's balance the forces first. We'll have an up-down equation, and we're going to have a right equals left equation. Okay, now looking at our forces here, the only things that we see pointing upwards, there's over at the wall, whatever that Fy thing is. But now there's also a component of the tension. If we make our triangle over here, part of it points up. That's a 30-degree angle right there. So whatever the tension is times the sine 30 is the upward force, and then we have a total of 9 newtons of gravity pointing downwards. Right, left, let's see, pointed to the right is that force of the wall, and going to the left is that x component of the tension cosine 30 degrees. Okay, well, we can't quite find the tension from those two equations because we don't know what those forces at the wall are. However, we do have this new condition. Anything trying to make the bar spin clockwise relative to the hinge has to be balanced by any kind of torque being created going counterclockwise relative to the hinge. Now, if we choose the hinge as being the axis, and we now use this new expression that we have to find torques created by forces, Fr sine of some angle. If you notice, let me change colors here. These two forces over at the hinge, the Fx and the Fy, those are not producing any torques. Why? Well, in those cases, the distance from those forces to the axis of rotation, which is the hinge, is 0. And our torque equation would give 0 torque for those. The forces that are trying to make this thing spin would include the two gravitational forces, those two weights. For example, if you were to cut the string and gravity takes over, those two things are going to try to make it spin down this way, okay, in the clockwise direction. They don't move that way because the tension in the string, that upward pull, tries to spin the bar counterclockwise. Okay, so those things have to balance. Okay, let's use this expression for torque and figure out for the 4 Newton force. Okay, the force is 4 newtons. Now the distance from the axis of rotation to the center of mass, where the 4 newtons of gravity is acting, is half the length of the bar. Now, I'm not giving you an actual length. Okay, we're just calling it L. But just L over 2 is what that radius value is going to be. And now we need the sine of the angle between the force and the radius. Well, the radius line is just along the bar. Gravity, of course, goes straight down. That's a 90-degree angle. Okay, that's the torque. That's the torque caused by the weight of the bar. Almost an identical thing we have to do for the 5 Newton weight hanging out there. The big difference is it's the full length of the bar away from the axis, okay, away from the hinge. And that too is going to be a 90-degree angle between the radius along the bar and gravity going down. So those are our clockwise torques. The tension, that's our force trying to make it spin counterclockwise. Well, that string, where is that tension being applied to the bar? Well, it's at the end, okay, a full length away from the axis of rotation. And now we need the angle between the radius line, which is the bar, and the string. Well, that's a 30-degree angle according to our picture. So tension times the full length times sine 30 would be the torque that the string is producing. There's nothing else. That's our torque equation. That's why we didn't need a number for the length. The length drops out. So let's see. On the left-hand side, we have 4 divided by 2, that's 2, and 5. We have 7 newtons. And that's equal to tension times sine of 30, which is 1/2. And we've got ourselves the tension. 14 newtons. Okay. That's usually what we have to find in these sorts of problems. Sometimes, however, if we had to find the forces over at the hinge, well, we could do that now. We could take the 14 newtons and we could substitute it into the two force equations, and we could solve for the other two unknowns, which is the Fx and the Fy. I'm not going to do that here. I mean, I'll let you do that if you want to practice, but that would be the strategy. What I really want you to focus on, though, okay, A, does the old stuff make sense? Okay, we've got our force diagram. Do those up, down, right, left equations make sense? It's pretty normal of what we do. But in particular, does this new condition here, balancing torques, does that make sense? We're using torque as force times a radius times sine of an angle and applying it to this specific picture. And that allows us to find out what that tension force is in the string. Okay, there's all sorts of variations on a theme that you could dream up for these sorts of pictures, but they're all going to be done the same way. Balance your two forces, balance your torques, and that's where we have to go now that we have rotation as a possibility. I hope this helps. I hope it makes some sense. And until next time, we'll see you later.